Hello my scholars, you're welcome to my school YouTube channel. My name is Emmanuel and today we'll be looking at atomic structure and bonding in chemistry. Please don't go anywhere, stick around and we'll be right back. You're welcome back to my school YouTube channel, and like I said earlier on, today we'll be looking at atomic structure and bonding in chemistry. Under that, we'll be looking at the particulate nature of matter, we'll be looking at the works of Dalton, Millikan, Rutherford, Moseley, Thomson and Bohr. Also, we'll be considering atomic structure, electronic configuration, atomic number, mass number and isotopes. Also, we'll be considering shapes of the s and the p orbitals. Also, we'll be looking at the periodic table and periodicity of elements. We'll be considering also the variation of the following properties, the trend of the elements in the periodic table. We'll be looking at ionization energy. We'll be looking at ionic radii. We'll be looking at electron affinity. We'll be looking at electronegativity. Also, we'll be considering chemical bonding, the types of bonding that we have. We talk about electrovalent bonding, we're talking about covalent bonding, metallic bonding, hydrogen bonding, and so on and so forth. And we'll be looking at the van der Waals force. The van der Waals force is a special kind of force, and we'll be considering that also. And lastly, we'll be looking at shapes of simple molecules. Now, let's get down to it. Particulate nature of matter. Remember that we talked about what matters are in a previous video lesson, and we said that matters are substances or anything that has mass and occupy spaces, and we said that they can exist in three states: in solids, in liquids and in gaseous state. Today we'll be looking at the particulate nature. What are the particles that made up matters, whether they are in solid state, whether they are in liquid state, whether they are in gaseous state. The concept or idea that matter is made of discrete particles is what we refer to as particulate nature of matter. There are several scientists that had worked and then they discovered that matter is made up of particles, which can be atoms, which could be molecules, or which could be ions. We'll be looking at the three of them, what the definitions of them are, and what particles we can find in them. Firstly, we'll be looking at atoms. What is an atom? An atom is said to be the smallest particle of an element which can take part in a chemical reaction. For instance, a piece of solid element like copper or zinc is ground into very tiny pieces. Okay, the smallest part of it, of that particle, is which can take part also in chemical reaction, is what we call an atom. If you get, a solid, copper for instance, and then you ground it, okay, and then you have them in particles, in smaller shapes. You take the smallest parts that you take from that, and then if you take it through a chemical reaction, it can still react, just like when you take the whole lump before you grind it, okay. Whatever you take from that, it can also act as, so for that smallest particle that can also take part in whatever reaction the big one before you ground it can take part in, we say that is an atom. Let's move on to the next slide. In other words, what we are saying is that the smallest part of an element that can exist on its own and still retain the chemical properties of the element is called an atom. Whatever chemical reaction that the element as a whole can undergo, the atom, the smallest part also, if you subject it to that condition also, okay, it will also go through that particular chemical reaction. So we say that is an atom, the smallest part. So the atom is made up of three main subatomic particles. There are three subparticles that make up the atom. We say we have the electrons that are negatively charged, we have protons that are positively charged, and then we have the neutrons that have no charge at all, neutron, okay, having the properties as shown below. Let's move on to the next slide. These are the properties of the subatomic particles. We have the first one. So what it means is that an atom can be further divided. You can have these three, that are present in it when you view it, okay, under some kind of devices, okay. We can have these three electrons. You will have just like an orbit, okay. Electrons are always moving around. We have the shell. We are going to look at the diagram now. So we have the electron that is negatively charged. We write it as the symbol this way. We have it's having a a relative charge of -1, -1. That's why we have it. We always write it as E, which is electron minus to the superscript of negative. So we write it down because it is negatively charged. And then we have a mass when it is compared to the mass of proton. That is why it is relative mass. It is 1/1840, and the actual mass of electron is 9.11 times 10 to the power -28. Also, proton is another subatomic particle that we can find in the atom of an element, and proton is usually positively charged, and it has this. You can see that relative charge is +1 plus 1, and then we have relative mass to be 1, and then the actual mass of proton is 1.67 times 10 to the power of -24. And then the last subatomic particle there is neutron. Neutron has no charge. That's why we write n to the power of 0. That is it. It has no charge. That's 0. And then it has a mass of 1, just like proton. Proton and neutron have the same, masses, 1 and 1. And then also, because they have the same masses, definitely the relative masses, definitely the actual mass will also be the same. So 1.67 times 10 to the power -24. Let's move on to the next slide. Now, this is the structure of an atom. You can have it. This is the center, okay. At the center of the atom of an element, we have the nucleus. You can see it here. That's why we have that. Nucleus is always at the center. And inside of the nucleus, we have two of those subatomic particles we talked about. We said we have 3 subatomic particles in an atom. We have electron, we have proton, and then we have neutrons, okay. Now, 2 of those 3 actually are found inside of the nucleus, okay. We have the proton present, and then we have neutron also present. Both of them make up the mass of that, because they are found at the center of the atom of the element. Because they are found at the center of the atom of the element, they carry the mass, okay. They determine the mass of that particular atom of the element. So in other words, neutron and proton are found inside of the nucleus. And then we have this. You can see this spherical, this spherical shape. Those are shells. We call them shells, or we call them orbits. Shells or orbits, okay. We have the electrons. You can see it always revolving around the shells, moving around the cell, just like the planets, okay, move around the sun, okay, move around this. So that's why we have it. So the electrons are always moving on the orbital or the shell, moving around that way. And then, depending on the type of element, we have different numbers of shells that can exist. As we move on, you will see the different shells we have that can have in the atom of an element. Let's move on to the next slide. The second particulate nature of matter is molecules. Remember, we said there are 3 particulate nature of matter. We have atoms, we have molecules, and we have ions, okay. So we talked about atoms already. Now, molecules. A molecule is of a compound or element is the smallest particle of a compound or element which is capable of independent existence. We are saying of compound element because we can have molecules that exist as compounds, like H2O. H2O is a compound, okay, but that is actually the molecule of water, okay. So we can also have a molecule existing as an element. If we have a diatomic element, we can say that is also a molecule. So we can have hydrogen molecule, that is H2, nitrogen molecule, that is N2, or oxygen molecule, that is O2, and so on and so forth. So a molecule of a compound can be said to be the smallest particle of that compound which is capable of independent existence. It can exist on its own. It can go through the other reactions. So like I said earlier on, a molecule may be composed of atoms of the same elements or atoms of different elements. For example, a nitrogen molecule, N2, we have 2 molecules of nitrogen, combining together to form that nitrogen molecule. Okay, so that is the same atom, the atom of the same element combining together to form a molecule, and then that contains 2 atoms of nitrogen, also oxygen, and so on and so forth. Then we also said a molecule of water contains 2 atoms of hydrogen and 1 atom of oxygen. So there are 2 different types of atoms here that are combined together to form this molecule. So this is the molecule of a compound. Okay, we have 2 molecules of hydrogen and then 1 molecule of oxygen. Molecules of compounds together, okay, and then this is molecule of the same atom combining together to form that molecule. So we can have molecule existing in this form of element and the molecule of a compound as well. The number of atoms present in each molecule of an element is what we call atomicity. The number of atoms, of course, as the name implies, atomicity, atom, okay? The number of atoms present in each molecule of an element is called atomicity of the element, and this number is usually very, very small. It's usually very, very small. So different elements, atoms of elements have different atomicity. Let's look at the next slide. You can see this table here. We have the type of elements, we have the non-metals like argon, okay? Argon has a symbol, we have looked at that before, has a symbol of Ar, and then we have it being monoatomic. Monoatomic means just 1 atom. Okay, that's why we say it is monoatomic, just 1. Is that you say the atomicity is 1, or you say it is monoatomic. We have helium also, of course, that's a non-metal. Okay, that also has a symbol of He, and then it is also monoatomic. We have oxygen, is diatomic. You can see that's why we have this symbol, you know, this way as O2, the formula H2. All of these ones that has this, these are their atomicity is 2 usually. Okay, you can see that here. But look at phosphorus. Phosphorus is P4. So it means it has 4 molecules that are combined together. So the atoms, the molecule of the atoms is made up of 4 different, you know, atoms that are combined together to form that. That's why we say it is what? It is, okay, that's an error there. So that is 4. The atomicity is 4, or we say it is tetraatomic. Either you say tetraatomic or you say polyatomic. Okay, so we have also elements such as sulfur. You can see sulfur, this will interest you. Sulfur is S8. So it means about 8 different atoms can combine to form the molecule of sulfur. Okay, and that, of course, we cannot say we have ultraatomic. There's nothing like that. So instead, from 4 upwards, we have polyatomic. From 5, we say polyatomic, 6, 7, and so on and so forth. So you can have that polyatomic. We have sodium is a metal. Sodium is just Na, that's monoatomic. You see iron here, monoatomic, and so on up to this point. So these are the different atomicity of the elements that we have. Let's move on to the next slide now. The third particulate nature of matter aside atoms, molecule, is the ion. What is an ion? An ion is an electrically charged atom or group of atoms. Okay, it is formed as a result of either loss of electron or gain of electrons. The electrons lost or gained are equal to the valence of the ions. The amount of electron that is lost is equal usually to the valency. That's why you see when we are writing Na, the ionic state of Na, we say is Na plus. So that's plus 1. Okay, so that means it is just 1 electron that is actually given off, okay, that is lost, okay, to become that. So there are 2 types of ions. We have the positive ions and the negative ions. The positive ions are what we refer to as cations, while the negatively charged ions are what we refer to as the anion. You have examples of positively charged ions here that are cations. We have sodium ion, you can see that positive, potassium ion positive, you know, copper ion positive, zinc ion. In short, all metals are usually referred to as cations. They are positively charged. Okay, and then we have negatively charged ion here. We have Cl, negative, minus, oxygen, 2 negative, sulfur, 2 negative, F2. So in other words, if you look at this, these are non-metals. So non-metals usually are negatively charged. So they are referred to as anion. So a cation is formed when an atom or group of atom loses electron. When an electron is lost, we said a cation is formed. In other words, a metal will lose an electron to become positively charged. Okay, any substance, okay, element or a metal that loses an electron will become positively charged. On the other hand, anyone that gains electron, the one that gains electron becomes negatively charged. Okay, that is it, like an irony of life. You should expect that when it's losing electron, it should be negative, right? And then when it's gain, it should be positive, but it's the other way around. Okay, when an atom, by the time we get to bonding, you will understand why we have it that way. So negatively charged ion are what we refer to as anion. You always see them having a negative charge. So you can see potassium here, okay, losing, that is negative, losing one electron, and then, like I said, once a metal loses electron, it will become positively charged. So you can have the same for sodium, Na minus E minus, losing one electron, we have Na plus. The same thing happens for all of this. So for copper will be Cu minus 2E minus, because we have 2 electrons. Okay, copper is going to lose 2 electrons, it becomes Cu minus 2E minus, then we have an arrow to have Cu2 plus. So which means it has lost 2 electrons and then it becomes negatively charged. Let's move on to the next slide now. Now I want to look at the works of some scientists on atomic structure, the structure of an atom. The first person we'll be looking at is Dalton's atomic theory. What does it say? Dalton's atomic theory is the idea put forward to explain what an atom is. It was first postulated in the year 1808 by a scientist called John Dalton, and then he came up with some speculations. He came up with some theory, and then what does it say? About 5 of them. We are going to look at them. Those were the works of Dalton. Okay, let's look at the first one. It says that matters are made up of small indivisible particles called atoms. So we are going to see the reason why this definition of matter will no, or this theory about matter will no longer hold. Okay, so that was the first thing he said. The second one, he says that atoms of a given element are all exactly alike in every aspect. That the atom of a particular element is the same thing in every aspect like every other one. So the third one, it says atoms can neither be created nor destroyed. Remember, this looks like the law of conservation of matter or mass. Okay, that matter can neither be created nor destroyed. So atoms can neither be created nor destroyed. That was what Dalton said. The fourth postulation was around the combination of atoms. He said atoms combine in small whole numbers, saying if copper is to combine with oxygen, so they are supposed to combine in small whole number. And the fifth one is all chemical changes result from the combination or separation of atoms. That all chemical changes came up as a result of the combination or the separation when atoms combine together, or when atoms of a compound are actually separated. Okay, that chemical changes eventually will result. So let's move on to the next slide now. Don't forget that when any scientist come up with a theory or with a postulate, okay, it will be verified by other scientists. It will not just be taken hook and hook, or it might be in operation. It can be accepted for some time, but with time, people begin to improve on it and modify those theories to ensure that it stands. So now there's a recent modification of Dalton's atomic theory. Now the first theory is said, remember, it said that matters are made up of small indivisible particles called atoms. But Rutherford disproved that. This statement has been proven wrong by Rutherford discovery. What does it say? It says that atoms are made up of 3 subparticles, the protons, electrons, and the neutrons. We just looked at that when we were talking about the subatomic particles of an atom. We said they are made up of a proton, they are made up of electrons, and they are also made up of neutrons. So if those 3 things can still be gotten from an atom, so why should you say that matter are made up of small indivisible particles? So if you can still get proton, electron, and neutron from a matter, then why do you say it's indivisible? Something indivisible, you should not be able to get anything, but we can get this. So Rutherford was able to, prove that wrong, that, oh, I was able to come up with 3 orders of atomic particles you can get from matter or from atom, and then there are protons, electrons, and neutrons. So that makes that to be modified, that actually matters are not indivisible. Okay, the second one was about atoms of a given element are all exactly alike in every aspect. That was what Dalton said. But the discovery of isotopes, okay, isotopes are atoms, 2 or more atoms of an element that have the same atomic number but different mass number. So if they have the same atomic number but different mass number, how come you say that all a given element are all exactly alike in every aspect? So that statement was actually proven wrong and unacceptable, because if you look at chlorine, this is an isotope of chlorine, this is another one, they have the same atomic number. You see these numbers that are written as the subscript are actually the atomic number, then the ones written as the superscript up here are their mass number. So they have the same atomic number and different mass number, so they become isotopes. Okay, so although they have the same atomic numbers and chemical activities, they differ in their number of neutrons. So that makes this theory, that postulate, not to be acceptable. Let's move on to the next slide. The third one was about atoms can neither be created nor destroyed. This statement still holds very true for ordinary chemical reactions as it is embodied in the law of conservation of matter or mass. Remember, we said that law of conservation of matter says that energy can neither be created, or matter can neither be created, or mass can neither be created nor destroyed, but it can be transformed from one form to another. So for an ordinary chemical reaction, this we hold. But in cases where we have atomic fission, okay, changes that occur as a result of atomic fission, okay, when we have one atom and another atom combining together, that's fusion. When we have one atom, okay, and another atom reacting together to form a bigger one, that is what we call fusion. But we are talking about atomic fission now. We have a bigger, element, atom of an element that splits, undergoes radiation, and then it splits into smaller ones. So we discover that in atomic fission, that particular element, the radiation will destroy the atoms of that particular element that is involved, and then the nuclei will now be broken down into smaller units to form a simpler atoms, and then it means that atoms are eventually created. But this is saying that atoms can neither be created nor destroyed. So, but if we have atomic fission or nuclear fission, okay, breaking down of a bigger nucleus or atom of an element, once it undergoes radiation, it breaks down into smaller units, and those smaller units will be the nucleus of another entire element, atom of another element. Of course, energy will be given off. So in that situation, this also proves. So we said this is true for only ordinary chemical reactions, but this law does not hold when it comes to radiation, radioactivity, okay, because we will form new atoms of another element. And the fourth one is actually that atoms combine in small whole numbers. Well, number 4 theory is still acceptable, okay, for most elements in inorganic chemistry. Okay, but if you talk about organic chemistry, no, that does not hold, because the statement, is no longer accepted, because carbon can form very complex organic compounds, that do not react in small whole numbers. For example, we have complex organic compounds such as heptane. Heptane has 7 atoms of carbon with 16 of this. Now, if you look at this, this is not a small whole number. This is 7, this is 16. The ratio is not in whole number. If it were C7H14, okay, that would be ratio 1:2. So that is a whole number ratio. We have octane, C8 and this. If it is where C8 and H16, okay, that would be ratio 1:2. But now this ratio will not give us a whole number. So this does not hold when it comes to organic chemistry. But for inorganic chemistry, well, it is fine and it can still hold. Now we've come to the end of the preview of this video lesson. If you want to have access to the full video, please click on the link in the description below that takes you to my school website, where you have access to view the full video, and then you subscribe. And in the full video, we'll be talking about atomic structure, we'll be looking at electronic configuration, we'll be looking at bonding, and so on and so forth. I hope you enjoyed this video. If yes, please don't forget to click the like button, hit the subscribe button, and tap the notification bell to keep you informed once we upload our next video lesson.